cover some of the key concepts in analyzing polynomials. It's kind of a starting point for us, so it's going to review a number of topics, many that you've seen in Algebra 2, some that you'll also see in my multiplicity video lesson. So some of this I'm going to skip over a little bit. We'll also then walk through the investigation that you did on polynomials, and then work forward to the notes on section 3.2. So, starting off, what's a polynomial? Well, when written in standard form, a polynomial is something that looks like 4x to the fourth plus 3x squared plus x plus 9, or 5x to the sixth plus 4x cubed minus 3x plus 2. Anything of that nature where you're doing what? You're having a variable raised to a number of different powers, all with possible coefficients in front. Not always will we have terms in every power or every degree, so to speak, but this is basically what a standard polynomial is. It's a bunch of terms in x to different powers with coefficients sitting in front of them. When you graph this type of polynomial, it's going to be smooth, continuous. Now that exact shape, we're going to work on figuring out how to draw that, but for the moment, just note a polynomial is always something that's continuous that you can draw with never having to stop drawing. The degree of the polynomial, when you're written in standard form, is always the highest power that you happen to see. So the examples that I did, this happens to be a 4th degree polynomial. This happens to be a 6th degree polynomial. The degree of a polynomial is going to determine some important things about the shape of our graph. Now, you can also write a polynomial in factored form, where you just have it as a bunch of individual factors. So for instance, 3x minus 6, x plus 2 squared, x minus 4. That's an example of a factored polynomial. Note that sometimes factors can repeat themselves. Here's another one, negative x minus 6 cubed, x plus 5 to the fourth, x minus 7 cubed. Relatively complicated, but again, that's a factored polynomial. And so one of the important things that we'll have to do here is when we get a polynomial is to actually figure out how can we factor it. That'll be another thing that we'll do later in this unit, doing some more complicated types of factoring. When you have something in factored form, the degree of the resulting polynomial comes from adding the degrees of the factors. So this first factor is, or first polynomial in factored form, degree 1, degree 2, degree 1, 1 plus 2 plus 1. That would be a 4th degree polynomial. My last one, degree 3, degree 4, degree 3. This would be a 10th degree polynomial. Now, again, talking of factored polynomials, look at this form up here, x minus r1, x minus r2, so on and so forth. r1, r2, these are the roots. They are the values of the polynomial that set it equal to 0. Sometimes we'll find out roots repeat themselves, all depending on just, hey, what type of polynomial have I been given? We talked about, and I encourage you to watch the video on multiplicities, talks about all the different types of behavior. What does our graph do at the roots? And also hand in hand with that is going to be what's the end behavior of our graph. We can figure out as x approaches negative infinity, where is the polynomial coming from? What was y approaching? And similarly, where was it going to at the end when x was approaching infinity? What's happening at the far right-hand side of our graph? What's the y coordinate doing? Well, what we're going to find out is the combination of the degree of your polynomial and the leading coefficient. Let's talk about that for a second. The leading coefficient, when you're looking in standard form, is find the highest degree term and look at the multiplier on that. So for instance, in our first polynomial that I gave here as an example, what are we seeing? 4x to the fourth. The leading coefficient happens to be a 4. 5x to the sixth. That's the high degree term. The coefficient is 5. The leading coefficient is 5 in that example. So what I encourage you to do is take a look, and what you're going to find out, whether that leading coefficient is positive or negative, is going to determine, in conjunction with the degree of the polynomial, the end behavior. In these two examples, just look for the constant that's outside of all the factored terms. Leading coefficient for this polynomial is 3. Leading coefficient for this one is negative 1. And one other thing that we'll talk about, and you'll see this as you go through your graphs, is turning points. A turning point is any change in direction when you go from increasing to decreasing, or decreasing to increasing on your polynomial graph. Anytime you've done that, you have gone through what is called a turning point. And again, it has to be a full and complete change of direction for you to have a turning point. So these are kind of the key pieces that I wanted to walk through for this unit. What we then gave you was this sheet, the investigation of graphs of polynomials. We gave you a series of printed out graphs as well. This happens to be for the second page, but here's the graphs for the first page that let you analyze all the different functions. You could see end behavior just looking at these. All the different pieces that you were asked to identify on these charts. Hopefully you've completed this. If not, you can check the answer key against your answers. But what we're going to do now as we walk into section 3.2 is start to analyze some general results. We can use these tables and some of the conclusions that we made in all of these different problems to lead us into what we're going to do in section 3.2, our notes on polynomials. So one of the first things that you're asked to do is look at all those answers that you got and consider some end behavior. And here are some sample graphs, and what you noticed is the following. We asked you, hey, if I gave you an odd degree polynomial, hey, here's an example, an odd degree polynomial and a positive leading coefficient, what was your end behavior? Where was y going? And we did that on these notes that you see for section 3.2 with all the different combinations of degree, odd or even, and positive or negative leading coefficient. So basically there's 4 combinations. And in those 4 combinations, you can see the end behavior. Just go ahead for safety's sake, fill in some arrows here. Give me a second to do that. But what you saw on this, again, is stuff you saw in Algebra 2 last year. Your end behavior, where you'll start drawing your graph and where that arrow goes, and when you're going to finish drawing and where your end arrow, so to speak, goes to, is determined by the degree of your polynomial and the sign of the leading coefficient. Visually, you can see it all here, but at the end of this note sheet, I've put together this little extra summary that went along with some of the multiplicity pieces. If you have an even degree function with a positive leading coefficient, you're going to have y approaching infinity both on the left side and the right side as x approaches negative infinity, as x approaches positive infinity. We're going to get away with being able to use arrows as kind of an informal notation here because we're drawing graphs this time. So this is going to be a useful shorthand for us. It's not definitively how we define end behavior, but for the purposes of what we're doing in this unit, it's going to help us. If we have an even degree polynomial with a negative leading coefficient, we're going to have the function approaching negative infinity on both sides. When we have an odd degree polynomial with a positive leading coefficient, our function will have downward end behavior as x approaches negative infinity. It will have upward end behavior as x approaches positive infinity, down, up, informally. And finally, an odd degree polynomial with a negative leading coefficient will have up, down behavior. These arrows let us know, hey, on the left side, where do I start drawing my graph? Where is it coming from? And on the far right, the rightmost arrow tells me where do I draw my arrow when I'm all the way, so to speak, done drawing this function. So that's what we're looking with here. So we can combine that and start using that to help us out in some other pieces of analysis. And there were a couple other things to come back and highlight as you look at the graphs. One, what do you know about the relationship between the number of turning points and the degree of the function? Well, it turns out, as we look through all of these, go back to the sheets just for a second, our turning point number is always less than the degree of our function. Sometimes it's really close. Sometimes, gee whiz, hey, there's a graph x minus 1 cubed that had absolutely no turning points. Well, the bottom line in all this, oops, and one that I happen to miss here, let's just fill that in. There's 3 turning points for this. The bottom line is the number of turning points and the degree of the function, it turns out, is following. The maximum number, the number of turning points, first and foremost, is always less than the degree of the function. And the biggest value that you can have for turning points is going to be degree minus 1. Degree minus 1 is the lowest number of turning points that you can have in any type of graph that you do. So very quickly, I'm going to go ahead and answer a couple questions that we have here. A function that has a leading coefficient that is negative and a fifth degree polynomial. Well, in that, we know that this is a up-down type of behavior. I'm going to have a fifth degree polynomial. Well, there's tons and tons of polynomials that we could do. I'm going to do the following as an example. Degree 5 negative leading coefficient. I'm going to have just a single root. And if I have just a single root, well, my end behavior is going to have to be right here because I'm never going to turn around. I can't go back to any more roots. And so I could do a traffic circle type of behavior. And so if this was x equals negative 3, I actually could have the graph of x plus 3 to the fifth. That would be a very good and useful example. Now, I could do something a little bit more complicated. Watch the following. Here's my behavior, and watch this. I'm going to keep plowing through time and time again. Time and time again. What do I also remember? Hey, I got to finish going down. Time and time again. Plow through again. I'm going to turn again. And what do I notice? I have 5 roots. Again, I'm going to make up my values here. Let's say that's negative 3, that's negative 2, that's positive 1, that's positive 2, and that's positive 3. What's this factored thing look like? Make sure I finish my end behavior, by the way. That looks like a whole bunch of roots with multiplicity of 1. X plus 3 to the first, x plus 2, x minus 1, x minus 2, x minus 3. That's a legit polynomial that does everything that I'd be looking for here. It has fifth degree. And what's the other thing that's kind of neat? Hey, notice how many turning points there are. 1, 2, 3, 4. One less. Remember, every time you got to hit a root, to get back to that root, you're going to have to make a turning point. You got to turn around to hit your next root. Now, I could draw other things in between. There's tons and tons of different polynomials that I could have used for this example, but both of those work. Hey, a degree 6 and a positive leading coefficient. Well, what do I know about that? This is going to be a up-up behavior. Hey, I could handle this with a very, very simple graph. Take a look at this. Let's assume that's a positive 1, my x-coordinate. I just drew x minus 1 to the 6th. That's a degree 6, positive leading coefficient. That's perfect. Hey, let me try a different one. Remember, I got to start up high because I'm up behavior. I also know what I need to connect to. Take a look at this. Here's a U-turn. Here's another U-turn. 3 U-turns. This is a legitimate graph as well. This could be maybe x minus plus 1 squared, x minus 1 squared. Let's call that x minus 3. Again, I'm just arbitrarily defining what these roots happen to be. There's a 6th degree polynomial. Works good too. Notice fewer turning points. But again, 1, 2, 3, 4, 5. There's still a fair amount of them that you see out there. Number of turning points still less than the number of degrees associated with the graph. Okay. Hey, what do you notice about the degree of functions and the number of zeros? Well, what you should notice as you break yourself down into factored form is that the number of zeros of the function is going to be equal to the degree of the function. You go back and look at all the different problems that you did. Now, some of you might say, well, wait, the number of zeros over here, this is a 3rd degree polynomial. I only listed 2 zeros, a 0 at x equal negative 2 and a 0 at x equal 4. Well, here's what I want you to make sure you understand. Look at the multiplicity. The multiplicity tells you how many times these zeros repeat themselves. So it turns out the number of zeros is equal to the degree of the function, but it turns out that some zeros could repeat themselves. Some zeros could repeat themselves. If we go back to these examples that I did over here, hey, in this case, what do I have? X equals negative 3 is the only 0. It repeats itself. Well, this is to the 5th power. It repeats itself 5 times. Down here, what am I noticing? Each one of these roots, also a 5th degree polynomial, they only repeat themselves once. I had 5 different roots. So make note, the degree of a function and the number of zeros will be equal. Just note that some zeros might repeat themselves. Let's continue. We've already talked about multiplicity in our other video on multiplicity and minimum degrees. Let's take a look at a couple more quick problems. I'm not going to work through all of these. You take a quick look at it. But each of these problems you're given zeros at x equals -2, at x equals -1, and at x equals 1. And you're asked to match the behavior. So I'm just going to go ahead and choose one of these matching problems and kind of walk you through it. X plus 2, x plus 1 squared, x minus 1 cubed. So when I look at this, x plus 2, I'm going to need to find multiplicity of 1. I'm going to need to find a plow through. No plow through here. No plow through there. Well, these two graphs at least have plow through. I've already eliminated the 2 on this side. Right. My next piece is I need to look at x plus 1 squared. Well, what's that tell me? At -1, I better have U-turn behavior. U-turn behavior? No U-turn. That's a plow through happening here. So to match A turns out to be this. So by staring through these graphs, understanding multiplicity and understanding shapes, you should be able to get a good insight into how these different types of functions work. By the way, let's do a couple other quick things. This looks like a even degree polynomial with a positive leading coefficient. Why do we say that? Look at the end behavior. It's an up, up. Here's another example. That's an up, up. This also must be an even degree polynomial. Over here, what are we seeing? Gee whiz, we are seeing a difference in end behavior. This is going to be a odd degree function with a positive leading coefficient. So there's a lot of work that we can do if we just kind of remember our little old table here that can help us as we work through a lot of these pieces. So again, let's do a little practice here. We'll just take one of these problems. I'm going to look at this problem that I see over here. And what am I noticing? I'm noticing 2 roots. I'm noticing plow-through behavior at each root. That's interesting. Excuse me, I noticed 3 roots. My fault. Just didn't look at the origin here. I see 3 roots. I'm seeing basic multiplicities at each. I'm seeing plow through each time. So it looks like I would have something of the nature, let's talk about this, x plus 1, x plus or minus 0 for the second root. Again, multiplicity is 0. So I'll write it as x minus 0 just so you see it like in factored form. And then x minus 3. Each of these to the first power. Now the last thing I need to look for is, well, do I have a positive or negative leading coefficient? Well, my end behavior is up, down. And if I go back and use my handy little chart, who has up, down? An odd degree with a negative leading coefficient. And there we go. I've built this function. Negative x plus 1 times, called it x minus 0, just call it x minus 3. I can write this as x plus 1, x minus 3. And I have this whole thing identified. So make sure, look at all these other ones. We could do something similar. Here's an example of what looks like, hey, U-turn functionality. There's only 1 root. What can I do with this? Well, number 1, it's down-down behavior, so I know I must be an even degree with a negative leading coefficient. Well, there's my negative. Where's my root at? Looks like my root is at x equals positive 1. I must be x minus 1. What could I do? Minimum degree, I could say this is negative x minus 1 squared. If I want to be a little more creative, well, remember, multiplicity, that's U-turn behavior. That could be what? X minus 1 to the 8th power. Any even degree factor here could be used because of the U-turn type of behavior. Best result, give me the simplest answer. If I said, hey, what's simpler, x minus 1 squared or x minus 1 to the 8th, I hope you would agree that it'd be x minus 1 squared. So this is probably the best default answer to work with. This down here is an acceptable one for that matter as well. Negative x minus 1 to the 8th power does the job. But again, I prefer stay with the simplest value.